Okay. Let's see, so 6:01. So I hope you guys had a chance to get to the lecture notes that I updated or revised. Okay. So do you have any questions from section 3.1 before I continue 3.3, and also we will go to 3.2. Based on the schedule, we're supposed to do 4.1 also, but since I'm giving a quiz today, so I don't know if we will have time to get to 4.1. Okay. So are there any questions from 3.1? No? Okay, if not, then I'm gonna try to share the lecture notes, okay, and see if it works out fine. Okay, so if you see anything unusual, please let me know. And if I cannot resolve the problem, then I may have to switch to my Microsoft book. Yeah, because I don't have experience using iPad Pro with this stuff, but I will give it a try. All right. Okay, so share screen. Start broadcast. Okay, let's see if there is a problem. So you guys see anything yet?
We see screen broadcast and Zoom, and there's a timer under.
Let's see here.
Oh, now we see it.
All right, now you see the notes, right?
Yeah.
Okay, good. Okay. So let's try this. So as you can see, if you compare the handwriting from the old notes to this one, it looks better, much better. And I can write more easily too. All right, so let me fold this down so I can start writing. Okay. So this is where we stopped last time. Okay, let me see. Hold on, okay. Okay, so we are supposed to see when I use iPad Pro, then I don't have, you see normally I have that pointer in purple, the round purple. I think I can move around, but I cannot find it on here. So let me see if you can, if I use this. Oh no, oh no. Then you don't see the pointer. I forgot all about it. So what should I cannot. Okay. Oh, okay. So I guess when I do this, you can see it. Okay. So I use that eraser, but I better not erase anything. Okay. So here we need to find out the concentration. So for this one right here, we know that it is 0 pound per gallon of salt coming in because it is pure water coming in. So right here, how much salt is coming in? Okay, then we have to find, so the amount of salt coming in depends on how much salt you have in the tank at that particular time, right? So I give you the formula for the concentration? I thought I did, right? I didn't I give you that in section 3.1? No.
Was that the one where it's the amount of salt over the total volume?
Yes. Where did I give you that? I remember that.
I think it was 1.3.
Oh yeah, 1.3. Okay, somebody just came in. Yeah, she wants students. Okay, all right. Okay, so at this moment, you can see that in the tank here. Okay, let's take care of tank number 1 first. So tank number 1, you have 0 pound of salt coming in for every gallon. Now, when it comes out, well, you have to be careful here, all right? Okay, so the concentration is it always, is the volume always 50 gallons in the tank? You have 2 sources of solution coming in and 1 source coming out. Is the tank always 50 gallons?
Yeah.
Yes,
Why is that?
because the rate in equals the rate out.
Very good, because there are 4 gallons of liquid coming in, but 4 gallons of liquid coming out. So the tank always contains 50 gallons. Okay, so that's the volume. But what about the amount of salt in the tank at time t? Because right here, you know that the concentration, we want to get the amount of salt come in the tank over the gallons, over the volume, which is 50 gallons at all time. What is the amount of salt in the tank at time t? You don't know that? It's right in front of your eyes. Remember how we found the concentration? The amount of salt in the tank at time t divided by the volume of liquid in the tank at time t. What is the amount of salt in the tank at time t? It's right there. We define it right there. What is it?
X1 of t.
Yeah, okay. So you see how important it is for you to remember to always define your variables when you work on something like this. So we define the variable here. X sub 1t represents the amount of salt in this tank at time t. So that's how we find the concentration at time t, right? So it is X sub 1 of t pounds. Okay, so that is the amount of concentration, amount of salt in the tank at time t. Okay, how about, now let's go to tank B. Tank B, we have something coming in, right here, but there are 2 outlets, one right here and one it comes out here. So it comes out here at 1 gallon per minute. But what is the concentration of salt that is leaving the tank at that particular time? Well, again, to find out the concentration, you take the amount of salt in the tank at time t divided by the volume of liquid in the tank at time t. What is the volume of liquid in the tank at time t?
X of 2 of t pounds over 50 gallons.
Very good. Okay, X sub 2 of t pounds of salt at time t divided by the volume of liquid in the tank at time t, which is also 50 gallons. Now, sometimes it is more than 50, sometimes it is less than 50, and you have to figure out what that function is, okay? But in this case, it is always 50 because you see right here, 4 gallons per minute coming in, and right here it leaves 3 gallons per minute and another 1 gallon per minute. So that is a total of 4 gallons leaving the tank and 4 gallons coming in. So 50 gallons is always a constant there in the tank. All right, so you have that. Now, how about right here? It lives at 3 gallons per minute, but how many pounds of salt is leaving the tank per gallon from this outlet? Remember, we are talking about at time t for the entire system, because the I actually erased the off. Okay, because the problem is just set up a system of first order differential equations for the amount of salt in the tanks at time t. So we talk about at time t. So at time t, we want to take the amount of salt in tank B at time t divided by the volume of liquid in tank B at time t, which is what?
Still x sub 2 of t, right?
Yeah, because that's how much salt tank B has at time t. You see right there from the definition, right there, right? X sub 2t. Okay, you guys were thinking too hard. Okay, you think it was like something else, like something weird in Mars? No, this is about time t. So just understand that to find the concentration of salt in tank B at time t, we take the amount of salt at that time divided by the volume at that time. So at that time, tank B has x sub 2t of t pounds, and the volume at that time t, which is 50 gallons. Okay. So now let's get a differential equation for tank A. Okay. So what is the amount of salt? What is the rate of change of salt in tank A after t minutes? So after t minutes, all right, at time t, right? Okay. The rate of change of salt in tank A depends on how much salt is coming in, okay, per minute. Because if you look at this one right here, you have to know what the unit is. This is x over t, so x is pounds over minutes. So let's go to the right and kind of remind yourself that, make sure the unit is pounds over minute, because we are trying to find out the rate of change of salt, which is the number of pounds per minute. So the number of pounds per minute of salt in the tank depends on the number of pounds per minute of salt coming in minus the number of pounds of salt coming out per minute. Okay, so the formula is rate. So it's equal to the rate of salt coming in. I'm going to write rate in minus rate out. If you want to, you can make a note. Rate here means rate of salt, right? Coming into the tank and leaving the tank. So if you look at tank A, how many sources are coming in to the tank?
Just one.
Just one? Look at tank A.
Well, only
There's
one source
two.
of salt.
No, how many outlets are there? How many valves?
There's two input.
2, right? Right here. One of them is right here, and another one is right there. So there are 2 of them coming in. So you have to add those 2 together. So for the first one, so let's do that. So for the first one, okay. So how did you get? So make sure you get pounds per minute. So for this one, how many pounds of salt per minute can you get from here?
0.
Okay, but let's write down everything so we can follow. Okay, so we know that we're gonna take the concentration, which is 0 pound per gallon, right? So it's gonna be 0 pound per gallon, or per 1 gallon. If you want to, you can write per 1 gallon. Okay. Times, and it is coming in at a rate of 3 gallons per minute, right? So 3 gallons per minute. So 3 gallons for every 1 minute. So that is from this valve right here. Now you have to add it to this one because both of them are coming in, right? So you add. Now the second source up here. Okay, so it comes in at x of 2 pounds for every 50 gallons times 1 gallon per minute. Okay, so you multiply these two, these two together. Okay, so I have, we'll just write x of 2. Okay, x of 2 pounds over 50 gallons times 1 gallon over 1 minute. So those are coming in, right? Now minus coming out. So what is coming out? How many pipes are there for the liquid to come out of tank A?
One.
Only one, which is right here. So you just multiply these two together. Okay, you multiply those two together. You have x of 1 pounds over 50 gallons times 4 gallons over 1 minute. Okay, I'm going to take this away. And then check to make sure that you always get pounds. So that's pounds over minute. Okay, so let's see here. So let's reduce. So you have gallons over gallons, that's out. Gallons over gallons, so you get pounds over minutes, and gallons over gallons you cancel out. Okay, so let's get your final differential equation. So what you have, so from here, dx of 1 over dt is equal to what? The first one is 0. 0 plus x over 50, right? X of 2. So that is 1 over 50 x of 2 minus right here 4 over 50 is 2 over 25. So 2 over 25 x of 1. Okay, so that is the rate of change of salt in tank A. And of course, the unit is pounds per minute. So now let's go to the second tank to get the rate for x of 2. So the rate for x of 2, again, it's the same, is the rate coming in minus the rate coming out. So rate coming in minus the rate coming out. Okay, and again, this is rate of salt. Okay, so you know that the unit is, again, has to be pounds per minute. Okay, so let's figure out the rate coming in. So looking at tank B, can you tell me how many sources are coming into tank B?
One.
One, which is this one right here, right? So you can multiply these two together to get the number of pounds per minute coming in. So you have x sub 1 over 50 times 4. So that's, okay, so you have x sub 1 pounds over 50 gallons times 4 gallons over 1 minute. So that is the rate coming in. How about the rate coming out? How many sources?
One.
One. Living tank B, there's only one?
There's two.
Oh,
Two.
yeah,
This
two.
we see it's living right here. You see the arrow? And then also right here, it is living tank B. Okay, so there are two of them. So you have to add the amount that is leaving, the amount of salt leaving the tank here, and the amount of salt leaving the tank here to get the total rate coming out. Are you all following? Yes, if you understand how to set up a system for this, for this problem right here, then you know most of them are just similar. Okay, so the whole idea is rate in minus rate out. That's all. Okay, so for the top valve, it is x sub 2 over 50 times 1, right? So x sub 2 over 50 pounds. It's a good habit to write the units every time. Okay, so you can know whether you got it right or not. So that is from the valve on the top plus the one on the bottom right here. X sub 2 over 50 times 3. Okay, so x sub 2 pounds over 50 gallons times 3 gallons over 1 minute. Okay, so what is dx sub 2 over dt? If you simplify, you get 2 over 50, 2 over 25 x sub 1, okay, minus what? What do you have over here? That's 1 over 50 x sub 2 plus 3 over 50 x sub 2. So 1 over 50 plus 3 over 50 is 4 over 50, right? So 4 over 50 is what? 2 over 25. X sub 2. Okay. And again, the unit is pounds over minute. Okay. So I asked you, what is the system? Actually, in this case, so the system, you just put the two together. You put this this equation and that equation right there together, you get your system. So your system is dx sub 1 over dt equals 1 over 50 x sub 2 minus 2 over 25 x sub 1. Okay, and then d x sub 2 dt is 2 over 25 x sub 2 x sub 1, I'm sorry, minus 2 over 25 x sub 2. Okay, so that is the system. But that's not it. You have to indicate the initial, okay, amount of salt for each tank. So for tank A at time 0, how much salt is in the tank? initially?
25 pounds.
25, and for tank number 2, it is 0, right? So you have 25, and for tank 2, it is 0. Okay, so the system, which is actually an initial value prompt, is this one right there. Okay, so that is the system. That's how you set up. Now, if you had a chance to get to my revised notes for this section, that you have everything here, right? If you did not, that's okay. Just leave it. You don't have to copy these. Okay, just write example 2 and take notes, and then you can go back home, and when you get the notes, you know what the examples are. Okay, so let's talk about predator-prey, competition, cooperation, relationships. Okay, so when it comes to this, let me let me stop the share for now. Okay, so we can talk about this a little bit. Okay, so you guys, do you guys love watching? I guess it's called the Animal Planet, right, or Discovery Channel. Okay, I when I was younger, I loved to watch those, and I still do. Okay, on Netflix, I just watch them. Okay, so predator prey. So let's say on an island. Okay, let's say we have only 2 types of animals. All right. So can you give me an example of 2 types of animals that refer to a predator-prey system? That's easy, right?
A fox and a rabbit.
Okay, fox and rabbits, very good. Okay, very good. Or we can talk about lions and wildebeest, right, and so on. Okay, so that is a predator-prey. Okay, so the remaining part of this section is, by looking at a system of differential equations, how can we tell whether that represents a predator-prey model or competition? I'll give you an example on an island again, 2 types of animals, okay, that will give you a competition. Make you think about of animals that compete with one another, huh? It doesn't have to be on an island, okay? In a jungle, okay? Just come up with 2.
Probably
Lions and cheetahs.
yeah.
Okay, lions and cheetahs, or lions and what is that?
Like a hyena or something like
Yeah, hyenas. Okay, there you go. Okay, so that is a competition, right? One time when I asked this question, a student said lions and tigers. Do you think that's right?
No,
Do they compete?
I don't think they're in the same ecosystem even.
Yeah, they don't even live in the same environment, right? Okay, so when the student said that, I said, oh, okay, I would recommend you to watch Animal Planet, so, right? But that's fine. It's okay. But he came up with the right idea, but unfortunately, lions and tigers don't live together. How about cooperation? Around your house. It doesn't have to be far in the jungle. Wow, cooperation. That's hard, huh?
Us and spiders, because they trap bugs so we don't get bed bugs.
Do they eat the same thing? If
Sorry?
they eat the same food, then they don't cooperate, right? They fight
Oh.
for the same food. Okay, so that's my question. So make sure you come up with two things that are really helping each other to survive. Okay.
Like flowers and bees.
Yeah, you can use those. Yes. Okay, flowers need bees, right? Okay, and bees need flowers. So yes, those two cooperate, and so on. Okay. So you get an idea. So now you look at the system. You get to be able to figure out whether the system represents a competition, a cooperation, or a predator-prey. Okay. And better than those, that I can give you a system about a man and a woman, and you describe to me how much the man loves the woman and how much the woman loves the man or hate the man and so on. And what is it that he has to do in order to get more love from her? Okay, and vice versa, by using differential equations. You see, now suddenly a person who is good at math can be a love counselor, a romance counselor. Okay, so you set up a differential equations and you start advising, okay, your clients. Yeah, but make sure you don't talk about differential equations because you're going to confuse them and they're going to leave you. Okay, so you lose your pay. All right. Okay, so let's look at the examples that I provide and see if we can figure out. But before we do that, it's better for us to do the problem, and then hopefully you remember the stuff that you learned from calculus 1. Okay, because see, differential equation is about derivatives. See, we talk about rates all the time. Okay, so you need to remember all the properties of derivatives. Okay. All right. So let's go to this one right here. So in this case, you have two equations. You know that t is time, so x and y would have to represent the birds and the insects. But how do we know which is which? Okay, so let's analyze. So let's look at the first differential equation. Okay, so 1. Okay, so you can look at the first one. So for dx dt equals this. Oh, I'm missing a number. 0, 0, xy. It should be 0, 0, 1. Okay, 0, 0, 1. So 0, 0, 1, xy. So let me point out this term right here so you know what that means. Okay, when you have a term that has a product of two populations, okay, like this, that means it tells you this is when population X and population Y are interacting with one another. Okay, so that's what it means by a product of two populations. That means that's when they interact. Okay, so in this case right here, for this differential equation, if the Y, if population Y wasn't there, what can you tell me about population X? And vice versa. Okay, if population X wasn't there, you don't know about population Y because this is the differential equation that tells you about the rate of change of population X, right? So you want to talk about what happens to population X, right? Okay, because this is the differential equation involving dx dt. So you ask yourself, what if Y is absent? Okay, so for this population, okay, what happens if Y is absent? So let's say if Y is absent, what does it mean by Y is absent in terms of a number? in terms of a number, what does that mean?
Is it 0?
You could say
That
1
is
or 0. Yeah, 0.
that is y is 0, right? So if y is 0, then this differential equation becomes what?
Zero 0.3x, right?
Okay. All right. So if you want to know what happens to the population of x, then you want to know the rate, right? In this case, dx dt is equal to 0.3 times x. So is this term positive or negative?
Positive.
Positive.
Positive, because you talk about population x, you don't talk about negative population, right? So you know that this is positive. Now, if that is positive, what does it tell you? So that means the derivative of x is positive. That means x is what? When its derivative is positive,
Increasing.
is increasing. There you go. So from here, you know exactly what happens. Okay. So can you tell me x is for which population?
Insects.
Insects, right? Because if the y is absent, the population of x is increasing. That means if birds are absent, insects continue to grow because the birds are not eating them, right? Because they are not there. You see? So that's how you can tell, okay, by using derivatives. And then furthermore, let's look at the y, because we want to double check both, because they might not turn out to be both an insect, right? Okay, so that's why you need to check. So 2 5 zeros. 1, 2, 3, 4, 5, 7 xy. Okay, so right here, so this is the term that will help you determine, because that is when the two populations interact. Same thing up here, right? This is the term that tells you that they interact. Okay, so in this case, you want to study the population of y. So you want to find out what happens when x is absent, right? So if x is absent, that is x is 0. Then dy dt is equal to what? So it's from here, right? What is dy dt? Is negative 0.4y. Okay, so that tells you that this is a negative number. So the derivative is negative. The derivative of y is negative, which tells you y is what?
Decreasing.
Decreasing. So you see, now why is it decreasing? Because it is dying. The insects are not there for them to eat. So from here, you know that, so therefore, you know that x represents the insects and y represents the birds. Okay. So here, well, I just answered it for you, but let's just write it down. What happens to the insect population in the absence of the birds? So right here, in the absence of the birds, the insect population is increasing because its rate is positive. Make sure you say that, okay? So from part A, we know that in the absence, so you have to answer, okay, in the absence of the birds. Okay, that is y is 0, okay. The insect population. Increases because see right here, you see x of t is increasing. Why? Because dx dt is positive. Okay, that's how we know. All right. Okay, how about example 3? How can you tell? So you do the same thing, like look at equation 1, okay? So 1. Okay, so let's name this one equation 1 and this is equation 2, right? So with equation 1, it is dx dt. So we want to know what happens when the y is not there. Okay, so when y is absent. Okay. Okay, or no, let's no, not absent, because you see in this case with the y that they interact, and this is a positive term. Okay, so what is that telling you? So that means with the presence of y. Okay, what can you tell me about dxet? When y is present, is this getting less or more?
More.
More. That means dx dt is getting more, right? Because this term with the presence of y, this is a positive term. So you add that positive term to these two terms, then this is getting more. Okay. So how do we say it? Dx is better because the term, the positive term. Okay, so it should be positive. The positive term which is this term 0, 0, 0, 0, 2 xy is added. Okay, is added to dx dt. Okay, so that's what we know. Now let's study. Let's study 2. Okay, so what about 2? Two is dy dt. So we want to look at the term when y is interacting with x, which is this term. Is that a positive term also?
Yeah, that's positive.
Okay, so do you think y needs x to be present?
Yes.
Yes, because if x is present, it helps y, right? Because if x is present, then you have a positive term being added to this one, so your dy dt is better, right? So with the presence of x, okay, how to say dy dt is better because just the same reason, okay, so because the positive term which is 0.0006xy, okay, is added to dy dt. So you notice it's added to dy dt that helps the rate of y to be higher, right? So higher rate yields more population, or higher population, you see? So in this case, so what can you tell me about this model? Competition or cooperation?
Cooperation.
Cooperation. Therefore, this is a cooperation model. Okay. All right, and I'm going to leave part B for you to do. See if you can figure out. Okay. So we are done. All right, so that is 3.3. Now let's go to 3.2. So 3.2. It's kind of weird. I don't like to use the apps because I cannot adjust the time with the OneNote app. So I'm gonna go to my other laptop to change the time real quick. So 3.2. And they sync, they communicate. I'm using OneDrive, okay? So they communicate. So is on this one it shows 4:37, but I just changed the time on the other one. It's just 6:49. So let's come back and see. It's going to be 6:49 later, okay? But 3.2, we're gonna talk about nonlinear models, okay? But before we do that, let's review the population growth model, okay? So for population growth model, that we know the rate of change of the population is proportional to the population itself. All right. So you have that. Okay. Just spill water on the surface. I'm wiping it out. So you see how picky I am, even picky to myself. I have to zoom it to a certain number, which is 123. So that when I transfer these files to my other laptops, they fit inside the screen. So I have to remember the value. All right, so let's look at this one. So in this case, you have a system, and of course it's a population growth, because you know that the K is positive, right? When the K is negative, we talk about radioactive decay. So let's go ahead and solve this IVP. Okay, so to solve, you just separate the variables. So that's going to be dp over p equals k dt. And then you integrate both sides. You integrate both sides. So this gives you ln of the absolute value of p. And on the right-hand side, it is kt plus c1. So we did all of this in section 3.1, right? So, you know, we did all of that in section 3.1. Okay, so, you know, so that's going to give you. Okay, but remember when I give you a problem like this on the test and I say solve, make sure you show the work, okay? Okay, so on the right side, you have c e to the kt. So we did that already, okay? So now you need to find out what c is. If you want to find out what k is, you need one more condition, but in this case, we have only one, okay? We don't have two, so we can, so that only gives you the c. So when you plug in, so this one, so that is equal to p naught when t is 0, all right? So that gives you c equals p naught, okay? So that's what you have, okay? So p of t is equal to c, which is p naught e to the kt. So that is the population function for you. So once you have the function, you can find out what the population is at a certain time, okay? Provided that you know k, all right? Now, so k, what is k? We know k is a constant, but does it have a name? Okay, let's go over here. So from this differential equation, you can get k, and you know k is actually the derivative of p with respect to t divided by the population p, okay? So the k, in this case, we call it a relative growth rate, okay? So k is a relative growth rate, and I will explain to you what that means. Now, so then what is dp dt? What kind of rate is that? dp dt, we call it is an instantaneous, like in calculus 1, instantaneous, okay, growth rate. All right, so we're talking about relative growth rate and instantaneous, growth rate. Okay, so what is the difference? Okay, so for instantaneous growth rate, it tells you how fast the population is growing at a particular time, okay? It could be like it is growing so fast, like say 100 people in the year 2000, for example. So it tells you how the population is growing at a particular time. Whereas the relative growth rate, it tells you how the population is growing relative to the population size at that particular moment. Do you understand that? For example, if the population is 100, then the rate of growth is going to be a certain number. If the population is 1 million, then the rate of growth of the population is going to be a certain number, okay? And K is the number that helps us determine how fast the population is growing for each population size. Okay, so for example, let's say I'm just giving you an example. Okay, so for example, let's say if this is equal to, for example, all right, for example, 0.2. Let's say K is 0.2. Remember, K is constant, so it doesn't matter what the population size is. Okay, at a particular population size, dPdt is going to be some number, and when you divide the two out, you're going to get 0.2. So at a different population size, you're going to have a different derivative value, but when you divide them out, you always get 0.2 because K is defined as a constant. So what is I meant 0.02. Okay, this is too much. Okay, 0.02. So 0.02, if you write it as a fraction, then you can tell that is 2/100. So what that means is when the population size is 100, that means when there are 100 people on that island, then you know that the population is growing at a rate of 2 people per whatever the time is. If we talk about per year, then we say, then when the population size is 100, then the population is growing at a rate of 2 people per year. Okay, so that's how you interpret the meaning. Any questions? Okay, so it's important for you to know how to interpret the meaning. Okay, and knowing how to solve a differential equation is like 50% of the work. The other 50% is knowing how to interpret the meaning so you can pass on the information to the public so they understand what is going on around them. All right, and that is your job as a scientist, to do that, to help educate your people. Okay, so here is a growth. So when the population, initial population, let's say is P naught right here, initial population, you need to label your coordinates and your axis, right? It's not X, it's about time, right? And this is P of T. So this is a population growth, and that is actually an exponential function. So you know that it is increasing like this, right? So this is the function P of T. And we talked about that before. See, this is not a good model to use for human population because our population does not grow indefinitely, right? Because from the graphic, it says that the population increases infinitely. So that's not right, okay? Now, let's go to the next topic, which is the logistic model. So what is a logistic model? Now, by the way, population growth is population dynamics, okay? So now let's talk about logistic. So what is a logistic model? Well, scientists, when they see this model right here, they said, wait a minute, this model we cannot use this one for the human population, because for the human population, eventually it's going to level off at some point, right? So we have to come up with a different model to study the human population. So let's say, for example, if for the human population, if the initial population starts right here, you know it's going to increase very rapidly in the beginning. Okay, in the beginning, increase rapidly, but eventually it's going to level off. Okay, it's going to level off. So this could be an example of how a human population is growing. Okay, it could passes this dotted line, but when it comes back here, it has to come back down because it could increase it so much, but eventually it's going to come back down. And this happens to not just the human population, but to a lot of different models. Okay, so for example, if you start from up here, let's say you start from up here, let's say the population is up here, you know it's too much, because right here, what that dotted line tells you is that is the carrying capacity. Okay, so that is how much the environment can support. So it can only support this much, and you try to go beyond that up here, you know that we're gonna fight against each other for spaces, right? And eventually the population is gonna die out and gradually is gonna approach this number. Okay, hopefully we're not gonna want it to go approach here, okay, because we don't want it to go to 0. So this is T and this is P of T. So up here the graph is gonna be like this. So eventually it's gonna level off to this. Okay. Now it could so the graph of P from up here, it could go down, it could passes the dotted line, but eventually it's going to come back up, because you know that there's a cycle here, you know, it always reaches to the capacity. Okay, so this also works like, for example, you know, if you guys are into housing, okay, you buy, you know the home prices are so ridiculous now. Okay, people thought that it would go down because of COVID-19 and because of loss of jobs, but it went the other way around. It went the opposite way. Okay, the prices keeps going up, even those people lost their jobs, and because it's locked down, COVID-19, but people continue to buy houses. Okay, so, and guess what happens? Okay, so you buy too much, right? You buy too much, maybe up here, goes up here, and eventually it's going to come back down. Okay, so my prediction is sooner or later the housing markets are going to crash. All right, so if you are smart like me in this situation, don't buy a house now. Okay, there's no point for you to buy a house now, because you have to compete with other people to buy a house, and then later on it's going to crash, and then you lost your money, right? Okay, so don't do that, just wait. Okay, it's so crazy now, you know, like Florida, like in Texas, you know, if you buy real estate over there, you're gonna lose money because the property tax over there is very high, and that's why the home value there doesn't increase as much as the home value in California, because in California we have a limit how much the government can increase the tax, can only go up to 2%. In Texas, there's no limit. Okay, if you buy a house now for $100,000, and they charge you say from 2.5% to 4% property tax rate, and then next year if your house goes up to $1 million, they're gonna charge you that much money. Okay, they're gonna charge you based on the current market price. In California, they don't do that. Okay, if you bought a house for $100,000, every year they can only raise the value up to 2% of the year before. Okay, so that's how it is. So don't buy a house now if you can wait. Okay, or if you have the patience. All right. Now remember, I told you about a research that I did back in 1989 on the spread of the HIV virus in Fresno County, right? That is the model that we were using, logistic model. Okay. Now, so what does it look like? What is a logistic model? So let P of T represent the population size at time T, and L is a constant, which is the carrying capacity, okay? So which is the maximum number that the space can accommodate, right? So what is the differential equation that would represent this model right here? So here's what it is. It is equal to a constant K times the population size at that time. But let me just give you an example. Suppose I'm gonna sketch an imaginary state. Okay, let's say this is the 51st state of the United States. Okay, so let's say the state is gonna be like this. Okay, so that is the map of that state, and you know, so far it has P people. So P people, let's divide it up. So let's say we have P right here. That's how many people they are at the present. Okay, so let's use P. We don't have to just use P. Okay, so we're saying that this state right here currently has these many people. So the rate of growth of this population depends on its size at the moment, but it also depends on this empty space right here. Do you agree? Because people said, hey, there's land here, so we can develop more housing and so on. Okay, I think I have their students. Okay. All right. So it also depends on this. But remember, the entire state can accommodate how many people based on the given information? Can accommodate L, right? That's the can capacity. So if the entire state can accommodate L number of people, and we have P number of people so far, then how many more can the state accommodate? How do you figure out this out? What is this? What is this amount?
Minus P.
What minus P?
L.
L minus P. Very good. Okay. So the differential equation says the rate of change of the population P depends on its population size, but it also depends on the spaces available. Okay, so that means it also depends on L minus P. Okay, where P of 0 equals P naught is the initial population. All right. Let me see, I use that. So that, let me just this one right here. We call that the logistic model. That's what it means. Okay. So, example 1. I give you this logistic model. How do you find out what the carrying capacity is? To find out what the carrying capacity is, you have to write it in this form. That means in this form, you see inside the parentheses, you have L minus P. So if you think this is L, then that's not right, because you don't have minus P. You have minus 0.01 P. So, you know, you have to somehow do something so that you get only a P right here before you can figure out what the carrying capacity is. All right. So how do we do that? You have to make this one a 1, right? If
You
you want to
factor
make that,
out 0.01.
yes, very good. So you factor out, let's say, so dp dt, you're going to factor out 0.01. So let's see what you, so you have a p. So what do you have to put inside so that when you multiply out, you get back to 30,000 minus 0.01 p. 0.01 times what will give you 30,000?
30,000 over 0.01.
Very good. Okay. This is arithmetic, right? Okay, so don't think too hard. Okay, this is not differential equations. Minus 0.01 times what will give you p?
P over 0.01.
Good. Okay, so it's going to be p over 0. So it's going to be p over 0.01. Okay. So what does that mean? That means dp dt is equal to 0.01 p times, no, wait, I'm missing, it's not right, because originally we have, it should be just a p, it's just a p, not divided by, because when you multiply out, see, when you multiply this to p, you actually get 0.01 p, right? So whatever you do, when you multiply out, you better get back to the original differential equation. So now 30,000 divided by 0.01 is 30,000 with 2 more zeros. Right? And then minus p. Okay. So from there, can you compare with the logistic model and tell me what L is?
3 million.
Yeah, that is your L right there. Okay, that is your L. Okay. So the carrying capacity is 3 million. Capacity. And you're done. Okay. All right. Now let's go to problem 2. So for problem 2, we need to read the book. So I hope you have your book with you, or if not, let's see here, the book, problem 2. Oh, right there. Okay. So it says the number of the number n of people in a community who are exposed to a particular advertisement is governed by the logistic equation. Okay, so you have to use a logistic model, right? Initially, n of 0 is 500, and it is observed that after one, in this case, what is the time? It's right here. Okay, it's right here. it observed that after one whatever, and we're gonna get that, well, it's 1,000. So solve n of t, that limited number of people in community who will see that one is 50,000. It doesn't even tell us. Am I missing the time? Number of people who are exposed to a particular advertisement is governed by 0. Great. Okay. Now the author is going to update to the 10th edition, and then students will have to buy a new edition. That's what they do. Okay, so I guess we'll have to make up a time. We'll come up with a time. Let's say how about a day? Okay. So that's why I came up with days right here. All right. So initially there were 500 people seeing the advertisement, and then a day later there were 1,000. And we know that the carrying capacity is like, we know the maximum number of people who could see the advertisement is 50,000. So how are we gonna go about finding? Okay, finding n of t. All right, so it's the logistic model. So we're gonna write down the logistic model for it. Okay, so we have dn dt is equal to from here dn dt is equal to k n times the carrying capacity minus n, right? Okay, so that is the logistic model. Okay, so from here we can plug in k n. The carrying capacity is 50,000 minus n. And then we're going to write down all the initial condition, given conditions. So n of 0 is equal to 500, and n of 1 is equal to 1,000. All right. So can you tell me how we would solve for n? Separate the variable, right? Okay. So we're going to separate the variable. Oh, by the way, before I do this, let's make a note in your book, because if and make sure you don't do it, okay? Because if you do, you will not get credited for it. Because I do not want you to use the formulas right here on page 98. Because the use of formula is too easy. Okay, I want you to understand how to come up with the formula. Okay, so please don't do that, all right? On the test or courses. Okay, so let's go over here. So we're going to separate the variables. So we have dn over n times 50,000 minus n. And on the right side, this is k dt. Okay. So now we're going to integrate both sides. On the right side, it is easy, right? On the left side, you have to do some work. So can you tell me how we go about integrating the one on the left-hand side?
Partial fractions.
Partial fractions, very good. So you have to use partial fractions. Okay, so let's go to the right and find out what the partial fractions are. So you know 1 over n times 50,000 minus n. So this is a simple one. So you know that you should have two partial fractions. So So if you are not sure, you can just do it like this, right? And then B 50,000. Yeah, 50,000 minus N. Okay. And so you see, if you do this, if I put 1 over N here plus 1 over 50,000 minus N, and when I combine these two fractions, I'm going to get 50,000 in the numerator, right? The numerator, the original numerator is only 1, but if you combine these two, you get 50,000 in the numerator. So you have to multiply by 1 over 50,000 to make up. Okay. Or if you want to, you can just do all the work to get A and B, and you will get that. Okay, so you know that the left-hand side becomes, so that is the work that you need to, oops. Okay, so I'm going to separate this so we have more room over to the left. So this is 1 over 50,000 times the integral of 1 over N plus 1 over 50,000 minus N with respect to N. Okay, and then on the right hand side, you have the integral of K, which is KT plus C sub 1. Okay, so I'm going to multiply both sides by 50,000. Okay, on the left hand side, the integral of 1 over N is ln of the absolute value of N. And then for the second integral, it's going to be negative. On the right side, when I multiply by 50,000, I have 50,000 KT plus 50,000 times C sub 1, which is C sub 2. Do you agree? Yeah, so if you want to, you can just make a note. C sub 2 is equal to 50,000 times C sub 1.
I have a question.
Okay. Yes?
Isn't it supposed to be plus ln of that?
No, because if you let U be 50,000 minus N, then the derivative of U is negative 1. Okay, that's U substitution.
Okay, thanks.
Okay, sure. So right here, you can combine these two ln to get ln of the absolute value of N over 50,000 minus N. And on the right hand side, and then the next step is to what? Everybody should know that word now, right?
Exponentiate.
Exponentiate. Okay, so you're going to exponentiate both sides. So I you know, when I give you a logistic problem model, you need to go through all of this, okay? Because I need to see if you know how to integrate by using partial fractions and so on. Because if I allow you to use a formula, then you know you can see a lot of questions on the test because you have a formula, which I don't want to do that. Okay, you can do that when you go to work in the real world. You can do anything you like, but here I want to prepare you, okay, for the real world. And so you need to know how to do all of these. All right, so you cancel out the E and the ln. You have the absolute value of this. And on the right-hand side, you have e to the c sub 2. Let's write e to the c sub 2 times e to the 50,000 kt. So from here, n. So I get rid of the absolute value symbol. Then that means on the right side you're going to have a plus and a minus, right? E to the c sub 2, and then times e to the 50,000 kt. Okay. So that gives you and everything here is going to be a new constant. I just call it c sub 3 for now because I don't know whether I need another constant. So I just call it c sub 3 and then like this. All right. Okay, so now what's next? I want to solve for n. So I need to multiply both sides by that factor 50,000 minus n. Okay, so n is equal to 50,000 minus n times c sub 3 e to the 50,000 kt. So imagine this is only one logistic equation, okay? And I told you my research was over 30 logistic equations. So it's a system of over 30 logistic equations. Okay, so now you just multiply out. Okay, yeah. So you're gonna multiply everything out and bring the terms containing n to one side. Right. So here you multiply out. You have 50,000 c sub 3 e to the 50,000 kt minus I'm gonna write like this. Have a minus n c sub 3 e to the 50,000 kt. So now I need to move this term. I need to move this term to the right. All right. Because so to the left, I'm sorry. You need to move that to the left. So when you move it to the left, what do you get? When you move it to the left, okay, move this to the left, and then you have n, and this the term contains n here. You factor out the n. So you factor out n, then you're gonna have 1 plus c sub 3 e to the 50,000 kt. On the right side, you have this. All right. Nothing new. Okay, this is just from calculus 2. So what is n? So n of t is equal to 50,000 c sub 3 e to the 50,000 kt divided by 1 plus c sub 3 e raised to the 50,000 kt. Okay. You can make it look better. And how do you make it look better? You can divide the top and the bottom by this guy. Okay. Let's do that. So now I'm going to divide the top. Let's not. Let's just do this. So divide the top by c sub 3 e to the 50,000 kt and do the same thing to the denominator. Okay, so what do you have? So n of t is, so on the top when you do that, then you have 50,000 left, right? over, and then you have 1 over C sub 3 e to the 50,000 kt plus, and then this one right here, this term, when you divide it by that, you get 1. So far, so good? All right, we're almost there. So n of t I like to write the 1 first. And then here I have 1 over C sub 3. And then the E on the bottom, I can write it on the top, raised to a negative power. Okay. All right. So now this term right here, this factor, 1 divided by C sub 3 is just another constant. Okay. So from here, you know, n of t is equal to 50,000 over 1 plus that constant c, okay, which is that is actually 1 over c sub 3, right? And then raised to this. Okay, so you just make one and make a note c is equal to 1 over c sub 3 if you like. Okay, so that is your general solution. Okay, so now you want to use the initial condition. So number 1, n of 0 equals 500 means 500 equals 50,000 over 1 plus c times e to the 0. Okay, so from here you can solve for c. So you have 500 times 1 plus c equals 50,000. So 500 c is equal to, what do you have? Okay, let me just do everything on the calculator real quick. Okay. So you know, you just divide both sides
49,500.
first. It's easier. Okay, you divide both sides by 500, right? Divide by 500, you get 100, right? And then minus 1, which is 99. That's faster. Okay. Now 2, you use this condition right here to find the k. So here's your general formula. So you put 1,000 for n, okay, and then 50,000. 1 plus c is 99. E to the 50,000 times k times t, which is 1. So that is just this. All right.
Should be negative, right? Negative 50,000?
Yes, negative. Thank you. Should be negative right there. Okay. And then you can just show all of this is just algebra, right? You can just solve. Okay. So from here you have 1,000 times 1 plus 99e to the negative 50,000 k, okay, equals 50,000. Okay, so I let you do this to get the k, right? So make sure you don't round off. Okay, so let me write. So you can do the work to check. Okay, so k should be 50,000 ln of 49 over 99. Okay. So therefore, here is the solution to the logistic model. Over 1 plus 99 e to the negative 50,000. I like to write like that, and then I say where k is, because I don't want to round off anything. Oh, that's good. Okay, you put the k in there. You see the 50,000 and the 50,000 on the bottom cancel out. Yeah. So yeah, so it's better for us to put in there. Okay, let me stop right here. All right, let me stop right here. And then you do it, and then you tell me what you have, and I can show you. I can tell you whether you got it right or wrong. Okay, so that's just algebra right there. Okay, so I couldn't get to 4.1, but that's okay. All right, now we're gonna take the quiz. Okay, so I give you 2 questions, one on solving by exact equations, and the other one by using substitution. Okay, so I'm gonna go to Canvas and